All right, let's take some notes on magnetism. Hopefully you've either downloaded the notes sheet from a couple days ago or it's on your computer where you can write on it. Um, like I said before, you can write on stuff and print it and write on it, keep it. Don't need to submit it to me unless I tell you to, or write on it on your tablet. Um, and just like I said, keep it for notes because we will be referring back to it over and over again as we go through some things on magnetism. So, if you have not done the magnetic stations virtual lab or whatever we want to call it from yesterday, I would suggest doing that before you go through these notes because I go back and reference those notes a few times during some of this stuff. All right, so there could be some confusion if you haven't done that yet or looked at that video yet. All right, so let's start out. We've seen this several times now in the things I've done is what is the source of all magnetic fields? Magnetic fields are created by moving charges. When we did electricity, static electricity, and things, we talked about, oh, hey, magnetism is a lot like electricity. Magnetic field is a lot like electric field, and there's a lot of similarities between these two. And the reason is real simple, all right? A magnetic field is a distortion in an electric field that is moving. So a moving charge has both electric field around it and magnetic field. So it's kind of interesting. So if you take a charged object and it's stationary and you put it in an electric field, it'll experience a force. If you take that same stationary charge and you put it in a magnetic field, nothing happens. Why? Because that charged object isn't moving yet. So there's no magnetic field around that charged object, so there can't be a force on it. So it's really kind of interesting. So that's basically all a magnetic field is. Electricity and magnetism are very, very, very closely related. A lot of the equations are similar. They have a electrostatic part to them and a magnetic part to them, but the magnetic part to them has to deal with when the object is in motion. All right, so why are some things magnetic? Things that can become magnetic have what we call magnetic domains. That's a property of them. So a piece of wood is not attracted by a magnet. A piece of aluminum is not attracted by a magnet. It's because wood and aluminum don't have magnetic domains. Okay, so magnetic domains are little microscopic groups of atoms that have magnetic fields aligned. Now, all atoms are moving charges, but what happens is some of the charges are moving in one direction, some of the charges are moving in other directions. And so what happens is their little bit of magnetic fields cancel each other out. So every atom in itself could be called a magnet. But when we put a bunch of atoms together to make, say, a block of wood, they cancel each other out. But a few items that can become magnetized are iron, nickel, and cobalt. That's because they have these groups of atoms that stick together with the same magnetic field. All right, so they don't necessarily cancel each other out so easily. So that's the really important thing about why some things can become magnetized and why some things cannot. All right, things that can have these magnetic domains as a property. So question number 3. Unlike charged objects that have positive and negatives, magnets have what we call north and south poles. These are just things that have been arbitrarily named, all right? And, plus and minus was something that Benjamin Franklin assigned to electric charges. I'm not sure who came up with north and south for magnetism. All right, but that's just the numbers, or not the numbers, but that's just the names that they gave them. All right, and then lastly, just like electric, opposite poles or charges in electric fields attract and repel. So that's why we can put one magnet near another magnet and it will spin away or it'll spin toward. That's why a compass works. A compass works because, like we showed in the lab, the compass will align itself with the Earth's magnetic field. And so a north arrow of a compass is always pointing toward the direction that we call north. It's aligning itself with a magnetic field of the Earth. We're going to talk more about the magnetic field of the Earth later on because it's kind of interesting to talk about. So let's look at magnetic domains and materials that have magnetic domains. So unmagnetized materials have their domains randomly aligned. So a piece of metal, a piece of iron, if I just pull out a piece of iron, like a nail, all right, it's going to have domains, but they're going to be randomly aligned, all right? Well, if I were to make that piece of iron into a magnet, all right, then what happens is those domains start to align, all right? So an unmagnetized iron bar is going to look like So an unmagnetized iron bar is going to have domains that just kind of point in all different directions. You can see like the tip of the arrow maybe would be the north part of the domain. Well, they're just going to all cancel each other out. They're like vectors, right? So if we added all those vectors, they would just cancel out to be pretty much zero. Let's watch a short video clip on magnetic domains. I'm going to cut this video off because this guy starts getting into theory that's a little bit beyond us. So we'll just go through the beginning of it, and when it fades off to nothing, that's because I chopped it off at that point.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 34. It's on the magnetic domains. In this picture right here, my daughter and I are both playing with ferrofluids, which are tiny little liquid magnets that can respond to a magnetic field. And so in this video, what I'm doing is I'm taking a magnet, holding it underneath the ferrofluid, and you can start to kind of visualize these magnetic fields. I can then turn it sideways, and you can even see the north and the south pole. And so these tiny little ferrofluids are made up of these 100 angstrom little magnetic domains, which are tiny magnets within the magnet itself. And so if you have ferromagnetic material in the form of a magnet, what you're going to get is a north pole and a south pole. Again, you'll never have just a north pole by itself or a south pole by itself, but if we were to look inside that ferromagnetic material, we would find that there are these magnetic domains, which you can think of as tiny little magnets, and each of those tiny magnets have their own tiny little fields. And so if you break a magnet in half, have you broken it? No, you've just created two magnets. And you could keep breaking it in half over and over and over until you get to the level of these tiny magnetic domains. And if these line up, if they align, then we've got an overall magnetic, ferromagnetic material. And they can do this by putting them inside an external field, or sometimes it'll just spontaneously or naturally occur. And so if we have a bar magnet, it's got a clear north and a south, we can make sure that it's magnetized by holding a compass up on either side. And you'll find that the south end of the needle points to the north end of the magnet and vice versa down here. Now if we break it in half, that bar magnet in half, what have we done? Well, let's use our compasses again. If we put them on either side, what you'll find is that we've now created a south pole at this side, and then we've created a north pole up here. So we could do this again and again and again, and we just keep making smaller and smaller magnets. So there must be magnets within the magnets that are causing that magnetism. And so you can think of it like this. In a block of iron, we've got all of these domains, which are going to be tiny magnets inside it. But if the whole thing isn't magnetized, they're going to be pointing in every which direction, and they're going to be separated by these domain walls. And so if you take something that's not magnetized and you magnetize it, what you're really doing is you're lining up all those magnetic domains. If they're all pointed in the same direction, then you've magnetized that overall object. And so a question that might jump to mind is, why do we even have magnetic domains? What's the purpose of having these tiny magnets within magnets? Well, it's an energy kind of question. So if we look at a magnet right here, it's creating these giant magnetic fields around the outside of it. And so what it's doing is using magnetostatic energy, is what scientists refer to it.
Okay, I think that was a pretty good explanation of magnetic domains. So if we started to take this unmagnetized iron bar and we made it slightly magnetic, well, what would happen? We would start getting the domains kind of in the same direction. And if you notice, I have them pointing toward the north. That's because inside of a magnet, the magnetic field goes from south to north. Outside the magnet, it comes out of the north and back into the south. So I'm getting my magnetic domain slightly pointing toward the north. And then lastly, as I make the bar really, really magnetic, all right, my domains are going to line up from south to north. Now we can't actually see the domains because the domains are very, very small microscopic regions. And so you need really, really powerful telescopes and things like that. Not telescopes, you silly goose. You need very, very, very strong type of microscopes, all right, to be able to look at the atomic structure of things. So they have to do stuff like, you can't even use light with these microscopes. You have to use like electrons to determine, what the how the atoms and stuff are arranged. You have to penetrate the stuff with electrons because light won't even be able to see the different magnetic domains. All right, so that's what we need to know right now about magnetic domains. The reason items can become magnetized is because they have domains, and then they actually become magnetic when the domains get aligned. So, as we saw before, yesterday's lab again, magnetic fields flow from north to south outside of a magnet and south to north inside a magnet. So here's the visual that we had yesterday. If you look, here we go, we got magnetic field flowing out of the north into the south of the magnet. And then what we can't see is that the field is traveling this way in the magnet. But if you were to use this as a solenoid instead, remember the solenoid is open on the inside, if we placed compasses in here, they would all point to the north. Right? And then they come back around this way. So magnetism has this property that it always works in like a circular type of pattern, around and around and around. That's the same as the picture in the very beginning that shows the magnetosphere of the Earth. Here, let me go back to that. Here's the magnetosphere of the Earth. We can see that the magnetic field, this is just a representation of it, but the magnetic field pretty much goes around in circles and circles and circles and circles and circles. Now, it's interesting to note that the magnets in the room overpower the Earth's magnetic field. That's because the field of the Earth is not very strong when we're way out by the surface of the Earth, but it's huge. It reaches way, way, way out into space. Why doesn't iron now become magnetized in the presence of a magnetic field? Well, it has to do back with those things called domains. All right, the nail can be made into a temporary magnet when it is in the presence of a magnetic field. The magnetic field aligns the nail's domains, making it a magnet as well. This is why the iron core in an electromagnet makes the electromagnet stronger. The electromagnet aligns the domains in the iron core and makes the magnet stronger because now you're using not just the coil, but you're using the coil and the nail's domains to be a magnet. So here's another video. Again, I'm going to chop this one off because what happens is they start out with, it's really kind of cool. They start with this really, really strong magnet and they pick up a bunch of ball bearings. And the reason they're able to pick up the ball bearings is because the ball bearings become magnetic temporarily in the presence of the strong magnet, and then the two magnetic objects attract to each other. All right, so watch this video and then we'll finish up in a couple of minutes.
Out came 7,000 metal balls, and then they brought out a heavy-looking wooden box. On its lid was a label that read "Danger." What's inside? Here it is. The world's strongest magnet, a neodymium magnet. They began to slowly lower the magnet. The metal balls started to twitch. but the magnet is still 30 centimeters away.
Wow! That's so cool!
The space between the magnet and the ground is packed with the metal balls. It's even more surprising to touch.
It's stuck! It won't budge! I can take a few off the surface, but the rest won't move.
Once the balls are stuck, they can't be removed by hand. They have to be pried off, like this. The neodymium magnet was invented by a Japanese researcher in 1983. Its strength took the world by surprise.
I just saw the demonstration, but could you explain why it's so powerful?
I'll use this to explain.
Okay.
This is an iron rod, and here are some iron balls. On its own, the rod doesn't have the power to attract the balls. But if you attach a magnet to the iron, like this, then the iron rod becomes magnetic. Detaching the magnet returns the rod to its original state.
Iron's atoms are actually small magnets, but because they don't point in the same direction, they cancel each other out, and the piece as a whole does not possess magnetic force. When a magnet is attached to the iron, all the mini-magnets turn to face the same direction. This causes the iron to become one big magnet. But once the magnet is removed, the mini-magnets in the iron return to their original direction, and the iron loses its magnetic force. This is where a metallic element called neodymium comes into play. Something amazing happens when neodymium is added to iron. Neodymium has the ability to keep the mini-magnets faced in the same direction. So even if the magnet is removed, the iron maintains a strong magnetic force. Thanks to neodymium, which allows iron to retain its magnetic force, the world's strongest magnet was born.
So what happens when a magnet's broken in half? Hey, guess what? Here we go, back to domains again. We learned this in the lab. All right, when a magnet is broken in half, its domains are still in the same alignment. Therefore, we just get two smaller magnets with the same north-south arrangement. Some magnets we call hard magnets. All right, so hard magnets are very, very strong magnets, and their properties are this. They're strong magnetic field, difficult to magnetize, and difficult to demagnetize. We have several of those in our room that we would be using with experiments right now. Weak magnets are called soft magnets, and as you might guess, their properties are pretty much just the opposites. Weak magnetic field is easily magnetized and easily demagnetized. That's why in yesterday's thing I showed you some compasses that were actually pointing in the wrong direction. The way the compasses were pointing in the wrong direction is they were weak magnets. And what happened is they were placed near a really strong magnet, and the really strong magnet actually demagnetized them and switched their magnetic fields. So what ways can you magnetize an object? When you magnetize an object, what you do is you align its domains. This can be done several different ways. Rubbing it with a strong magnet. I think the Modern Marvels movie showed rubbing a pocket knife with a magnet, and it made the tip of the knife magnetic. Leaving it in a magnetic field for a long time. That's, like I said, the compasses that are pointing the wrong direction in the classroom is because what happened actually is a physics teacher, not me, not Mrs. Stan either, but someone took a bunch of magnets and compasses and threw them in a box together. And so it remagnetized a bunch of our compasses so that they point in the wrong direction. So you shouldn't throw compasses and strong magnets in the same box. Another way is actually heating up and cooling something in the presence of a magnetic field. These are how hard magnets are manufactured. When a company manufactures a magnet, like neodymium or, gosh, I can't think of the other name, something oxide, shucks, Inconel magnets. What they do is they make this material, but it has random domains. Then what they do is they put it in a device that heats it up in a magnetic field and then cools it back off. And then what that does is the heat relaxes the domain so they're able to move around. The magnetic field aligns the domains, and then when you cool it off in the magnetic field, those domains are locked in place. I think I have a quick video now that just shows the magnetizing of a nail real quickly. Again, this is something we would have done in lab if we were able to do it. But it's just about a minute long.
Now this is an iron nail, which we have often seen. It is actually attracting this particular pin which is sticking to it. But how does this happen? It happened because we created a temporary magnet out of this nail. I will show you how this is done. We will use a single touch method. We need a bar magnet, iron nails, and pins. Let's begin. We will take this iron nail and hold it up. Since we are using single touch method, we just need one magnet. We will run this magnet along this nail from one end to another in one smooth motion as many times as we can. You need to take care that motion is uniform, has similar speed, and is not too slow or too fast. After you think you've dubbed a number of times, bring the nail near the pins that we have here. What do you see? The iron nail is attracting the pins just like a magnet. So the iron nail has got magnetized. Since the nail will lose its magnetic property after some time, it is considered as temporary magnetization. In the single touch method, a single magnet is moved along the surface of the nail in a single direction, end to end, many times. Now make as many magnets as you can with this method.
All right, ways you demagnetize something. Well, you can imagine they're pretty much the opposite of magnetizing. Demagnetizing occurs when we cause the domains to become unaligned. So it's kind of interesting. So here's a couple ways we demagnetize. You can just heat something up and just let it cool outside of a magnetic field, or dropping it. One of the interesting things I do in a demonstration is I take a nail and I make it a magnet by rubbing it, and then I pick up a bunch of paper clips with it, and then I throw it on the floor, and it no longer picks up the paper clips. Well, what happened is the shock of the vibrations going through that magnet, all right, caused it to become demagnetized. So dropping a really soft magnet would cause it to demagnetize. Like I said, heating it up, the domains are just going to go back to where they used to be, all right, and that will demagnetize something. All right, so I hope this one wasn't too long. I think the whole lesson will be about 15 minutes long when I'm done adding the videos. And so this is your next thing to work on. Again, like I've said before, just either copy these notes in your tablet where you can go back and look at them because you will get some questions on them. Or if you print them and write them on a piece of paper, that's up to you. Just keep it in your binder for use, because when we do any when we do any quizzes or things like that related to this stuff, obviously it's just all going to be open notes and everything. So the best you do at taking all these notes are going to be the, better for you. All right. So take it easy. I don't think I'll have any more videos this week. Well, let me take that back. I might have one tomorrow. We'll see. But that's going to be a pretty complicated one. So I think I'm just going to give you another short assignment tomorrow. Friday will be e-planning day, where we have to plan and you get to finish up stuff. So Monday we'll kick off with a brand new topic. Still magnetism. I keep saying tasm in weird words. I don't know what's wrong with me. Still magnetism. but I haven't had enough coffee yet today. I think that's the problem. Anyhow, have a good weekend.